This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Last Friday we discussed the refrigeration cycle, and similar to the other cycle, we discussed there are 4 components in the system, and dealing with 2 pressures. So. Refrigeration cycle sometimes is a bit confusing because you're dealing with a case which is against overall, globally against nature. But you're starting with a compressor, which will give you the input work. And then you compress the vapor and going through the condenser to convert the vapor to liquid. And in that process, you throw away a lot of heat to the high temperature reservoir, and then it's all become liquid, saturated or can be overheated liquid. Then going through this special device called the throttle or expansion valve. So this is a device basically allow you to drop the pressure, and we said because you're dealing with saturated mixture, you drop the pressure, you drop the temperature. Right, because temperature and pressure are like basically close related when you're dealing with the saturated mixture. And the process going through the throttle is quite special because there is basically nothing changed in terms of the energy terms. The heat transfer, the heat doesn't change. There is no work being done, and even the entropy doesn't. I shouldn't say anything about entropy. Enthalpy does not change. So this is an isentropic device, not isentropic. It's not a compressor or turbine. It's an isentropic device. So after that's why on the TS diagram we didn't draw a vertical line, and we draw a line like this. The entropy, if you're looking at the process, entropy actually increase in this process because this line is to the right, indicating the entropy actually increase in this process. Then the partially vapor, partially liquid mixture going into the evaporator. And the evaporator there, you're picking up the heat from the cold reservoir, and then you basically converting everything into vapor, then going through the compressor again. So on the ideal case or ideal refrigeration cycle is what we draw here. So you're working on this saturation dome in 2 of the states. And we also discussed what the actual refrigeration cycle look like. And I'm not going to draw here. If you already attend the workshop, you should have a better idea about how to draw an actual TS diagram. If you haven't, then you will have a chance in the next 2 weeks. Right. So one thing we discussed but didn't finish is about the different type of refrigerant. All right, probably can adjust this. So this is more about application side of this cycle, and we mentioned that the last generation of the refrigerant is something called the CFC or Freon. So that's basically, it's a compound containing chlorine and fluorine and connected with one carbon. So this one is being banned and mainly because it destroys the ozone layer in the upper atmosphere, which protecting the Earth's surface from too much UV light. So that one is not being used. The one being used is called fluorohydrocarbon. And one of the compounds have a structure like this. Basically, it gets rid of the chloride and they replace with fluorine there, and also you have hydrogen. So this is a compound that doesn't destroy the ozone layer, but more recently people are getting more aware of the global warming issue and the greenhouse gas emission issues, and then this compound has some downside, which means it has a much larger global warming potential compared to the carbon monoxide. So it's about 1,500 times of the global warming potential than the CO2. So basically, if you emit 1 kilogram of this kind of refrigerant, you are equivalent to 1.5 tons of CO2 to the air. So, but this one is currently still being used. So this seems pretty large, but if you consider the amount of leak of this kind of compound to the atmosphere, and overall it's not a very significant source. But people start thinking to replace this kind of refrigerant for the next generation. So this is currently being used, and this particular one is called R134A. So R is a refrigerant. So each of these compounds basically has an ID as a refrigerant. So this one called R134A. If you go to the property table, sometime you can just find this number. The one of the next generation one is propane. So if you're looking at the propane chemical structure, there's a 3 carbon and only carbon and hydrogen. So there is no fluorine even involved in this case. So this compound, as long as you don't burn it, it does not have global warming potential. But this compound has some obvious issue in application. Can you figure out in application? Yes. So this is basically a fuel, right? Propane is a fuel. If you go to the gas station, that's the auto gas. It's a major component in auto gas or LPG. So it's flammable. But in terms of other downside, it doesn't have the potential to destroy the ozone layer or having the global warming problem. But this is one of the things being proposed. Actually, in our lab, the refrigerant we use is propane. All right, so this one has an ID of R290. That's one we use in the lab. All right, so this is more on the what type of refrigerant we want to use. So in terms of application, the cycle we discussed here is a basic cycle. So if you want to use, it's enough for you to run the fridge at home or in office. So that's okay. But in industry, there is other applications which require deep refrigeration, or some cases is a cryogenic application, which is temperature is much, much lower compared to the freezer temperature in the fridge. So in that case, there is certain modification or certain variation of the cycle that needs to be implemented. So let me just write one. So one of the process is showing here, so which is called the cascade refrigeration cycle. So in this case, the idea is straightforward. So basically, you stack two refrigeration cycles together. All right. So it's like a relay. So you have one. So if we consider this is your normal one, the normal cycle running there. And then on the evaporator, which is supposed to be the cold spot for the top cycle, then it is served as the condenser for the lower cycle. So the lower cycle is running at certainly at lower temperature, using a different type of refrigerant, which have the phase change property, which working at a lower temperature range. So there, this refrigerant or this cycle is running at a lower temperature where its condenser actually is a hot spot for that cycle. Is have a heat exchanger set up as a heat exchanger with this cold spot on the upper loop. So in this case, you can consider it's like a relay. So on the cold side, then you can reach a lower temperature compared to you running with one cycle, one loop only. So that's can allow you get into a lower temperature. And the other way is this called the Lind process, which is a process invented by the company Lind. And here is a process basically to produce liquid gas. So if you consider, if you want to get a liquid nitrogen or liquid oxygen, their temperature is 90 Kelvin, so it's about minus 180 degrees C. So that's a very low, very cold temperature. So this type of process can allowing you to reach that low temperature. So basically, you have a high compression coming in and have the condenser there, then going through this heat exchanger to be so after the condenser. I shouldn't say this condenser because at this point it's not become liquid yet. So the compressed gas is got cooled first, then got cooled second, and then going through this throttling valve. Throttling valve, as I said, is a device to drop pressure, and drop pressure will allowing you to drop temperature. And after this throttling valve, you have a mixture which is saturated liquid versus saturated vapor. And the liquid, because it's heavier, collected at the bottom, then got collected. And the vapor is at the same temperature as the liquid, but it didn't got a chance to condense, then going back to this heat exchanger. So this vapor is very cold as well, help to absorb some of the heat from this compressed gas. So by this process, you can produce liquid nitrogen as well as liquid natural gas. So natural gas, the major component in natural gas is methane. So has a condensation point is somewhere around minus 160 degrees C. You're using this process, you can produce liquid natural gas, which is LNG. So if you saw some some truck which is carrying LNG. So this actually is a major, not major, it's one of the upcoming new energy that's being shipping around the world. Particularly Australia is one of the major exporter of the liquid natural gas there. All right, so these are the process which allowing us to reach a very low temperature. There is other cases where you want some cooling of a certain application, and in that case you can run something called air refrigeration. So this case using air as a refrigerant, certainly not involving air being condensed as a liquid. But it relies on a principle that if you consider the Carnot cycle, we said the Carnot cycle, if you run it in a forward way, it's an engine, right? You can use it as an engine. If you run at a reverse way, it can be a refrigeration cycle, right? So this one consider that based on this principle, any power cycle, if you run it reversely, it can become a refrigeration cycle or producing some cooling effect. That's the concept. You run a power cycle in a reverse way to producing some cooling effect. So that's the one of the major things. For example, if we have the TS diagram, if we draw the Brayton cycle, another one, there and there. So if you have the Brayton cycle dealing with ideal gas, so all air in this process, no phase change, you are starting from here, compressor, combustor, and then turbine going to here, right? If you run this process reversely, so if I go from here, I use a compressor to raise the pressure to that state. So compressor, input work, then because the gas got compressed, the temperature will goes up, right? If I have a heat exchanger to dump this heat away, QH, then going through a turbine to drop the pressure, and then at that state, the pressure is lower and the temperature is also lower. Then I can let it go through the low temperature reservoir to pick up some heat. So again, the idea is to run this power cycle in reverse way as a refrigeration cycle. All right. So this actually being used in reality, and in the aircraft. So for the aircraft cabin cooling, this actually is using this kind of process. So there you have a compressor. You have the compressor, compress the cabin air to a high pressure, and then going through a heat exchanger. So then you dump the temperature to the outside. Outside the aircraft, that's pretty cold, right? And then you're going through a turbine to drop the pressure and the temperature as well. And then the temperature become cooled, right? So this cold air can go in through the cabin and pick up the heat. I should draw it here. then going in the compressor again. So basically, it will take up the Q air from cabin. So when this air passing through the cabin, basically you're picking up heat and then going through the compressor again. So this one, you may wonder, the outside is very cold. Why not we just using the air outside in order to, why we are doing this, right? Because outside is very cold. Why we are doing this? Yes, that's very good. So for aircraft, the aircraft is a pressurized system, right? The air inside the cabin is certainly not connected to the outside. If you connect outside, all the air will be leaked to the outside. So you cannot you can using the outside, the cold air outside as the to picking up or to transfer heat to the outside, but you cannot directly using the air from the outside. All right, so that's a case where you can reverse the kind of reverse the power cycle and producing some cooling. And in this process, if I'm asking you, what about the COP compared to a process involving the vapor? What would be the COP comparison? COP in a vapor cycle involving phase change, and we said during phase change there is a huge amount of heat can be transferred during the phase change without changing the temperature very much, essentially no change in temperature. But in this case, the air there is no phase change for the air, so the heat that can be transferred during this process is much less compared to a vapor cycle. So this COP is low, but for the application it's okay because we cannot cool the cabin to the very low temperature, right? And it has the advantage in terms of you can using a pretty compact system to do this. You don't need to put on some heavy component on the aircraft in order to do this. Also, you don't need to carry the refrigerant, right? It's on the air, and air will be there anyway. So the plus would be the compact and no refrigerant needed. All right, so that's basically the end of the refrigeration cycle, and I hope you will learn more after the workshop and after solving the problem there. All right, so that's the end of chapter 3. We'll move to the next chapter, which is the other power cycle using steam. All right, so this is the second power cycle which we discussed, and the first one is the Brayton or gas turbine power cycle. As a power cycle, the useful output would be the shaft work, and it's also the working fluid here is steam. I mean, it's not just the steam. Certainly, part of the working fluid is water. So this is a vapor cycle. We will dealing with phase change in this process, just like the refrigeration cycle. Right? So while we study the steam power cycle, if you're looking at how electricity is generated today around the world, steam power or the steam turbine connected to the generator, that generate 60% of the total electricity being produced today. I mean, world average. So that's saying that's certainly a predominant cycle that have been involved in the electricity generation. The gas turbine cycle that we discussed, or the Brayton cycle, we discussed is also an important one, but it's not as important as the steam turbine. So gas turbine accounts for about 20%. And that's mainly because gas turbine using natural gas, and the natural gas historically is quite expensive compared to steam turbine, which is mainly using coal. Coal is cheap, and that's why it has been used predominantly for the power generation. But the gas turbine is in recent years the price for natural gas drops significantly. And the reason for that is a process called fracking. And that's relatively new technology where you can, certain natural gas is stored in rocks called shear. Those special type of rock, if you smash it, you can release the natural gas, and then they can be used for the power generation. And that process used to be very expensive, but now the technology has an advanced level. We can extract those gas relatively economically. So the natural gas price got reduced quite significantly in recent years. So other than the shear gas, previously the natural gas is naturally exists underground. So if you drill oil, and sometimes before you see the oil, you will see a lot of gas, because gas that's on top of the oil, and that really define you have reserve on the ground. But with the shale gas, the reserve is a lot, particularly in countries like U.S., which conventionally being considered pretty, like doesn't have much of the natural gas reserve. But now, because of this technology, it can produce a large amount of natural gas and actually drop the world natural gas price to a level which is never seen before. All right, so that's the gas turbine. And another important type of electricity generation that is using hydropower. So this is essentially the hydro turbine. This process, you directly convert the potential energy to electricity, or you convert the potential energy to the kinetic energy at the turbine and then to the electricity, right? So there's no combustion involved. This accounts for about 15%. A very significant fraction. And the world's largest hydro plant, how many of you know it, where it is? Yeah. Yes. That's the single largest. I forgot how many gigawatts it can produce. If I remember right, it's like 20 gigawatts of power it can produce. Yeah. So hydro is a significant amount in terms of the electricity generation, and the rest is 5%, including the wind turbine and some of the solar PV, which directly converts the light to electricity. That accounts for roughly 5%. So it's clear that the steam turbine is the most important way that we produce electricity today. All right, let's look at a video, which is a video which taken in 1940s, but it just I think it's still helpful in terms of showing how things works.
Light touches the finger, and darkness turns to light. An ounce of pressure from a workman's hand, and tons of iron and steel answer with the voice of power. Light and power. They move on wings of high-strung copper in the form of electric energy. Electric energy, of which almost 2/3 produced in the United States, is made with steam. Steam is the force that produces every year over 95 million kilowatts of power. And the machine that makes this high production possible so that it can serve our homes and factories and run our ships with efficiency and economy is the steam turbine. Did you ever wonder just how one of these huge turbines works? What goes on inside? How the magic of steam makes it hum with power? If we heat water until its temperature is 212 degrees Fahrenheit, it will begin to change from liquid into a vapor, which we call steam. Steam is strong stuff if we control it. If the kettle is stationary on the grill and we place a paddle wheel in front of the spout, the jet of steam will make the paddle wheel turn. But this is neither efficient nor powerful. So let's take a tea kettle with 4 spouts and a paddle wheel with many more paddles. The wheel moves more quickly and with greater force. In fact, what we see here is a very crude example of the impulse-type steam turbine, which is merely a series of paddles, or blades as they are called, being moved by the velocity of steam jets. There's another kind of steam turbine called reaction type. For instance, let's place this kettle on rollers and put the lid on it. This partly confines the steam, builds up a little pressure, and forces a jet of steam out the spout. The jet of steam will react with enough force to push the kettle in the opposite direction. When the lid is removed, the pressure is relieved. The jet of steam no longer comes out of the spout, and the kettle stops moving. Another crude example of the reactionary principle is shown by the force of a jet of water leaving the nozzle of a fire hose. If the jet has a high velocity, 2 or 3 firemen may be necessary to hold the nozzle. Of course, the modern, powerful steam turbine, whether impulse or reaction, or a combination of the 2 principles, is not nearly so simple, even though it operates on the same principle. It is a miracle of mathematics and precision engineering designed to meet the most exacting standards and built with the accuracy of a fine watch.
Okay, another video is about a more detailed look of the how a turbine works. Steam turbines.
steam turbine. Steam spouts from each nozzle at such high velocity that the driving force on each blade in the first moving row amounts to 200 pounds. In some turbines, this force may be as high as 400 pounds. These blades are scientifically shaped to get the greatest work out of every pound of steam. When the steam jet strikes a blade, causing it to move, the steam flows along the face of the blade, following its contour. By placing a set of stationary blades beside the moving blades to receive the steam and change its direction, causing it to flow again to another row of moving blades, added power drives the spindle to which the moving blades are fastened. When the engineers did this, they were merely employing the impulse principle which caused our paddle wheel to turn when the steam from the tea kettle struck it. Let's place another set of moving blades on the other side of the stationary blades to make further use of our rapidly expanding steam. When we've done this, we have illustrated the working of the impulse stage of a modern steam turbine. Steam from a boiler enters here and is directed through a series of jets against these blades. As the blades are forced to move, the steam is discharged on the opposite side through a set of stationary blades, which changes the direction of the steam. The steam being directed to another set of moving blades thus gives more power and speed to the revolving drum or spindle. Of course, a modern turbine is much more complicated than our simple diagrammatic pictures. In a large percentage of the turbines built today, both impulse and reaction principles are employed. Here, in slow motion, is the action of the steam in the blades of a reaction principle turbine. It is exactly the same as in our illustration of the rolling tea kettle. The blades in the reaction principle turbine are engineered to get the most power out of the steam flow as it moves through them. The steam moves through the stationary blades first, to be directed into the moving blades, which actually do the work. Now let us see how the impulse and reaction principles are combined in the modern steam turbine.
Okay, I think that's enough for understanding this. So same principle applied to the gas turbine. So you have what you're seeing here is called the rotating blades and the stationary blades. Basically, that's the rotor and the stator that we see in the gas turbine as well. All right. So the basic cycle that describe steam power cycle is called the Rankine cycle. So again, this is a basic cycle, and I assume it has been learned previously. So it's starting with a pump, with pumping liquid, and then going through something called a boiler. So the liquid being the high pressure liquid or compressed liquid being converted to steam at the boiler, and then going through the steam turbine. There it becomes mostly still mostly vapor and could containing some water afterwards. Then they're going through another device called the condenser. So that's a place where another phase change will happen to convert all the steam or vapor to liquid water. Then you're going back to this pump. All right. So this is a basic cycle for the Rankine. So if we call this is 1, 2, 3, and 4, you're dealing with a two-phase. The working fluid can happen in two phases. So at the pump here, that's the liquid, and then liquid, and vapor, and the vapor, mostly vapor. There could be some a small amount of liquid after the turbine. So the components in terms of pump basically is a device. In our discussion, pump is also an isentropic device. It's like a compressor, just to raise the pressure of the liquid. And the turbine is something we discussed before. Boiler is essentially it's a heater, or it's a, if you consider the ideal cycle, it's a process where heat is being added externally to the working fluid. So the boiler is basically is a heat addition device. And although today most of the boiler is burning fuel to generate steam, but it doesn't have to be burning coal. Any heat source that can supply sufficient amount of heat to produce steam can be used as a boiler there. So coal being used just because it's available in large quantity and it's cheap. So mostly it's coal, but not necessarily. You can burn natural gas. There is a natural gas, rather than being used in the gas turbine, it's being used to generate steam in a boiler to run on the steam cycle. So that's possible. And you can also burn biomass. So if you have a certain agriculture or forestry residue that is no other use, you can just processing them and burn them to release the chemical energy there. And also another important heat generator for the steam power plant is the nuclear. Nuclear reaction, as we said, is release the nuclear energy that bonding the subatomic particles. So that energy level is order of magnitude compared to combustion, larger. So in that case, you have the nuclear reaction happens, then you running water through it. Basically, that reaction is a heater to generate steam. All right. So that can happen. And also you can have other process. For example, you can use in solar or geothermal. And you just have to find a way to concentrate the solar energy to produce the high temperature in order to generate steam. And the geothermal needs to be high quality, which means the temperature needs to be pretty high in order to generate steam. So that's the boiler. And the condenser is another device where the phase change happens. So I should say the boiler is occurring at a condition which is a high temperature and pressure. And the condenser on the other end is a low temperature and the pressure. So if we're looking at what a condenser look like, so this is a picture showing in a steam power plant how a condenser look like. So if you know how a heat exchanger looks like, why it's not? So essentially, it's look like a heat exchanger. You have the steam coming in from one end, and in this case, later on we'll discuss this. Basically, it's a shear and tube heat exchanger. The steam is going through this shear side, and the cooling water basically from there, and then got condensed, then become liquid, then leaving here. So it's a shear side, which is outside the tube. And the water, cooling water, is going through the tube side, which is it has a header here, to going through these tubes, and then leaving from the other head there. So water is flowing in the tube side. So, but essentially it's a heat exchanger, and you cool the steam, or allowing the phase change happening there. And this process requiring large amount of cooling water. All right. If you remember the number I gave you, 1 kilogram of water So if you remember, the heat of vaporization for water is (2240) kilojoule per kilogram, right? And if you consider the specific heat of water, the Cp of water is about 4.2 kilojoule per kilogram, right? So this saying that if you have 1 kilogram steam, when it condenses, it will release this much of heat. If you're using water, 1 kilogram of water to take away this energy, the water will raise by 500 degrees C, right? That cooling water must boil by itself. So to avoid that, you need to run a large amount of cooling water. For example, if the temperature difference is 100 degrees C for the cooling water in and out, you need 5 kilogram of cooling water in order to condense 1 kilogram of steam. So there is a large amount of cooling water required in the steam power plant, and that's why you always see water near a coal-fired plant. So that's actually one of the picture here. So in order to cool the cooling water, so this cooling water takes away a lot of energy, and that needs to be cooled. Otherwise, how do you get more water for the next round, right? So one case is you install this power plant near a river or near ocean. Then you have infinite amount of cooling water available. But that's not always possible. So there is different ways that has been done to achieve that. One is using cooling tower. So this one is a chimney, which is coming from combustion, but this is not from combustion. So this vapor is all water vapor. So this called a cooling tower. So basically, those cooling water. So this cooling water going from the top of the cooling tower being sprayed down, and then the dry air is blowing from the bottom of this cooling tower. So when the air is dry, it wants to absorb moisture, and during that process, because part of the water, when it's going down, is being vaporized, and during the vaporization process, the temperature will drop, and then the unvaporized water getting down to the bottom of the cooling tower will have a lower temperature. So this is one way to dealing with the cooling of the cooling water, and the other way is if you don't have the ocean or river next to you, you can have a pond. So this actually is one of the power stations east of Melbourne, and that's been closed a couple of years ago. So it has a cooling pond there. It's a very large cooling pond. Basically, it just have the cooling water pumped into this pond, and then taking in the new like fresh water or cooled water for the next cooling, and then allowing the vaporization process on this pond by nature in order to cool the process. And in fact, one interesting thing is because this power station next to this pond, the water in that pond at a temperature which is around 25 to 30 C. And there is quite a bit of, to make use of it, there are quite a bit of tropical fish that are being fed there. And when this power plant is being shut down, people are really concerned because the temperature will drop. What's going to happen to those fish? And actually, we have a project then to calculate how soon when the power station shuts down, how soon the temperature in the pond will drop to the ambient temperature. All right, I think that's a good place to stop.